So we're going to talk about some different kinds of reactions. We talked about precipitation reactions. There are also acid-base and gas evolution reactions, and these can also occur when we've got the anions and cations swapping places. So acid-base reaction, also called a neutralization reaction, as the name suggests, we have an acid and a base, and they react to neutralize each other. And generally water is formed, but sometimes a weak electrolyte. A gas evolution reaction, as its name implies, evolves a gas. So a gas is formed that may be seen as bubbling or fizzing, or sometimes the gas has a color, like the gas we saw in that copper lab. So those are two more types of reactions. So we need to talk about what is an acid. We've talked about an acid as being a molecular compound where the first letter is hydrogen. Of course, there's more extensive definitions than that. The Arrhenius definition of an acid is a substance that produces hydrogen ions in aqueous solution. And this fits with the definition we used for nomenclature. So here we have HCl, which we would name as an acid. When that dissolves in water, it ionizes to form hydrogen ions and chloride ions. Let's think about what is a hydrogen ion. What is a hydrogen atom? What's in a hydrogen atom? How many protons? 1. And how many electrons? 1. So if a hydrogen atom loses 1 electron to become an H plus ion, how many electrons does it have? 0. And it doesn't have any neutrons, it just has a single proton. So a hydrogen ion is a bare proton. So that's not going to be very stable. It's not actually going to be found by itself anywhere. And so what's going to happen is that hydrogen ion, instead of floating around in this aqueous solution by itself, it's going to ride on one of the water molecules. I think of that hydrogen ion as being a very small baby. Very small babies, you see them out in public, but they're never by themselves, right? You don't go walking down the street and see a crowd of 5-month-old babies or something on the sidewalk, right? It's ridiculous. So the hydrogen ion is too small to be out by itself, and so it's always riding piggyback on a water molecule. When you put a hydrogen ion onto H2O, hydrogen ion plus H2O, you get this guy, H3O plus, that has the name hydronium ion. And so this is slightly confusing. I apologize for that, but chemists use H plus and H3O plus interchangeably. So sometimes we use this one, sometimes we use the other one. It's a little bit like saying, well, this is the baby and this is the baby being held by its mother. And so when I talk about the baby was there, we all kind of understand that an adult must have been there with the baby, right? The baby wasn't there by himself. So that's kind of how this works. So an acid is something that produces a hydrogen ion in aqueous solution. If there's a hydrogen ion in aqueous solution, it's going to ride on a water molecule and actually be the hydronium ion. So that hydrogen ion is a proton, and so we talk about polyprotic acids, many protons. That just means they have more than one ionizable proton, ionizable hydrogen. And they release them sequentially. They don't release them all at once. First they release one, and then the second one. So an example is sulfuric acid, which is on our list of strong acids. It is a diprotic acid, so we see from its formula H2. It's got 2 ionizable hydrogens. The first one is a strong acid. It will ionize completely. All of the H2SO4 molecules will lose one of their hydrogen ions. Losing the second one, though, it's a weak acid. The Arrhenius definition of a base is a substance that produces hydroxide ions. in aqueous solution. So an example would be sodium hydroxide, probably the most common base we use in the chemistry lab. This is an ionic compound. It dissociates, it's very soluble. We get sodium ions and hydroxide ions. Hydroxide ions are produced, this is a base. There are other bases such as ammonia. Ammonia doesn't look like a base from its formula because there's no OH in it, right? There's just some hydrogens and a nitrogen. This does produce hydrogen ions, and it does so by pulling up a hydrogen ion. It does produce hydroxide ions. It does so by pulling a hydrogen ion off of a water molecule. So it does produce hydroxide ions. We see that some bases will produce 2 moles of hydroxide per mole of base. An example of this would be something like calcium hydroxide. So when we put this in water, well, actually it's not going to be that, it's be this way. It's going to separate into its ions. There's a calcium 2+ ion, and we're going to get 2 hydroxide ions. So if we have 1 mole of calcium hydroxide, we're going to get 2 moles of hydroxide ions. So that would be like a diprotic acid, except that there's no word for these bases that have 2 moles of OH minus. And when they dissociate, the bases do so all at once. So this isn't going to lose 1 hydroxide at a time like the acids do. It's going to just completely fall apart. Any questions so far? So when a hydrogen ion from an acid combines with a hydroxide ion from the base, it forms water. And so if we look at that, so acids produce hydrogen ions in solutions, in aqueous solution. Bases produce hydroxide ions. If we have an H+ and an OH-, just putting those together as an ionic compound, you'd come up with HOH. You might say, oh, why does that look silly, right? Well, we don't write it that way. We write it H2O. But a hydrogen ion and a hydroxide ion will combine to form a water molecule. And here it's written out more nicely down there. So in an acid-base reaction, what we have happening is the acid is producing hydrogen ions, the base is producing hydroxide ions. Those are going to combine to form water, and the cation from the base, the anion from the acid, are going to combine to form a salt, an ionic compound. So we can think of this in terms of swapping partners with the ions, just like we did for precipitation. So we're going to put the hydrogen and the hydroxide and the chloride and the sodium, and we end up with water and sodium chloride. If we write the net ionic equation for this, well, the sodium chloride is aqueous. When we write the complete ionic equation, those would each be individual ions. And so the chloride ion and the sodium ion are both spectator ions. So if we go through and write the net ionic equation, we end up with this. And that is the net ionic equation for acid-base reactions, as long as the salt that's formed is soluble, which is usually the case. Any questions? So here we have pictures. So we're adding sodium hydroxide and hydrochloric acid, mixing them in this beaker. They're both clear, colorless solutions. They look like water. They're definitely not water, but water is the solvent. So in the HCl is a strong acid. All of these molecules separate into hydrogen ions and chloride ions. The hydrogen ions are too small to be out by themselves, so they're riding on the water molecule. So we see hydronium ions and chloride ions, and then all around are water molecules. The sodium hydroxide solution, this is a soluble ionic compound. It separates completely into sodium ions and hydroxide ions. When we mix these together, the hydronium ion and the hydroxide ion get together and form water. You can think of it this way. A hydronium ion is the same as a hydrogen ion plus a water molecule. The water molecule is just carrying this hydrogen around, this bare proton, because it's too small to be out by itself. So when this combines with hydroxide, the hydronium says, oh, here, you take the hydrogen ion. And this water goes off by itself. These two get together, and that was a weird plus sign, and form another water molecule. Probably the crappiest explanation of that I've ever done. So those become water molecules, which, are just among all of these gazillion other water molecules. And what we have left then are chloride ions and sodium ions. We've turned an acid and a base into literally salt water, because the acid and the base neutralized each other. So here's a list of some common acids and bases. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. These are strong acids. Strong acids are strong electrolytes. They separate completely into ions. There are 6 of them. You just memorize them. What helps a little bit is that these 3 are all in the same family: chlorine, bromine, and iodine. So those are the binary acids. Those are all strong acids. And then nitric, sulfuric, perchloric, I don't have a trick for that. You just have to remember it. The good thing is you memorize the 6 strong acids. Every other acid is a weak acid. So then you can identify strong acid versus weak acid, because if it's not one of the 6, then it's weak. So here's some other weak acids. And notice the formulas here. Formic and acetic acids both have more than one hydrogen in them, but only one hydrogen is written in the front. That's because that's the one ionizable hydrogen. This is a monoprotic acid. This hydrogen's not going to act as an acid. And here for the acetic acid, these 3 aren't going to do anything. For bases, strong bases are going to be metal hydroxides. So these are strong bases. They're metal hydroxides that are soluble. If it's not a metal hydroxide, something like ammonia, then it's going to be a weak base. Okay, so we're going to write a molecular equation and a net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. So this is going to go similarly to doing the precipitation reactions. We need to start out with the chemical formulas. Here they were given to us. So we have HBr, that's aqueous. And I have LiOH, also aqueous. I'm going to leave some space here in case I need a coefficient. And these are going to react. So what I'm going to do down here is I'm going to write the ions that this forms with their charges. So HBr ionizes to form hydrogen ions and bromide ions. And lithium hydroxide dissociates into lithium ions and hydroxide ions. Everybody okay with that? Then just like with the precipitation reactions, we're going to swap partners and see if any chemistry happens. So we've got the guy and the girl coming to a party, guy and the girl coming to the party, and they're going to swap partners and we'll see if they hit it off. So over here, I'm just going to write them with their new partners and put H plus and OH minus together, see what happens. Li plus and Br minus together and see what happens. Well, what do I get when I mix hydrogen ions and hydroxide ions? Water. So this is water, H2O. What's the state symbol? Can't be aqueous, right? Because water dissolved in water, but liquid. So, liquid, the water can exist as a solid or a gas also, but unless otherwise specified, we assume that this is going to happen at room temperature, so the water will be a liquid. And then I can write the formula for this, Li, that wasn't very good, LiBr. Is that soluble? Remember that table? The first row, lithium, sodium, potassium, ammonium compounds, always soluble, no exceptions. This is soluble, so I'm going to say aqueous, it's dissolved in water. I need a plus in here, and then I need to balance this. So I've got one bromide and one bromide. I've got one lithium and one lithium. I've got an OH and an H here, and those are the guys that came together to form water. So I don't need any coefficients. So that's my molecular equation. We could call that ME, molecular equation. Any questions about that? We're also asked for the net ionic equation. Once you become really familiar with this, you could look at that and just write it down, but we're going to assume that that's not happening just yet. So what we want to do is we want to look at these compounds in our molecular equation and ask ourselves, are these ionized in solution or are they intact? So anything that has AQ is potentially written as ions. This liquid we're going to write as a liquid. So H2O, we're just going to write H2O liquid. But this LiBr, that's a soluble ionic compound, and in the ionic equations, we write the formulas as they actually are in solution. So in solution, the lithium ions and the bromide ions are not hanging out together. They're thoroughly mixed around and they're free to move. So I'm going to write plus Li plus aqueous and Br minus aqueous. Soluble ionic compound separates into ions. Okay? Just kind of working backwards because sometimes that's more fun. Here's lithium hydroxide, aqueous. Also a soluble ionic compound. This happens to be the base, but it is a soluble ionic compound. So I'm going to write its ions separately. And having written these ion formulas here to help me predict what the products are, I don't have to do much thinking. All I have to do is say, well, do I write them separately or do I write them together? So here, this is an acid. The acids are the one kind of aqueous substance that might not be written as individual ions. If it's a strong acid, that means it separates into ions completely, so we separate the ions. If it's a weak acid, it only ionizes a little bit, and so we're going to write it as an intact molecule. Is this a strong acid or a weak acid? It's a strong acid. You know that because you memorize it, or you remember that I told you so. So because it's a strong acid, we're going to write that as separate ions. It's a strong acid. So what I've got here is the complete ionic equation. We could call that the CIE, complete ionic equation. How do we get the net ionic equation? Get rid of the spectators. So here's bromide and bromide's over there. So if I cross those guys off, because bromide is not actually getting changed, it's just hanging out watching the chemistry happen. Lithium is another one. I have lithium plus and lithium plus on both sides. Exactly the same. What I've got left are H plus and OH minus on the left and H2O on the right. Those aren't going to cancel each other out. I'm not going to cross them off. So for the net ionic equation, I'm just going to rewrite this without the mess of the crossed out spectator ions. And we sometimes call that NIE for net ionic equation. That's the net ionic equation. Yes?
So if the acid was a weak acid, you said you keep it as HBr acting whole? Okay.
Right. So if you have a weak acid, your net ionic equation is not going to be this one. But if you have a strong acid, it pretty much will be. Any other questions? Let's do one with a weak acid. So, oops. We're going to write down our formulas. So I've got HCHO2, that's aqueous. And I've got sodium hydroxide, also aqueous. And they told me that's a weak acid. So I'm going to pull these into ions and swap the partners and see what happens. And you might look at that HCHO2 and think, that's kind of messy. Let's do the sodium hydroxide first. So this is sodium ions and hydroxide ions. Now we have to go back and face this other one. This is an acid, and for the acids, it's that first hydrogen that comes off, and then you write whatever is left as the anion. So I'm going to have H plus, and then what, if I cover up the H, what's left? CHO2. Well, I'll just write that down. CHO2, and that must have a -1 charge on it because a hydrogen ion has a +1 charge. You don't know how to name that? It's okay. You just have to write it out. So now we're going to swap partners. See what happens. And as with all acid-base reactions, we're going to get H plus and OH minus. And I'm going to write those other two, the sodium and the weird one. H plus and OH minus give me water. It's a liquid. And to put these together, I'm just going to look at their charges and put them together, +1 and -1, so I just need to write them next to each other. Is that compound soluble? It's a sodium compound, right? All sodium compounds are soluble, no exceptions. It doesn't matter that we don't know the name of that ion. It's aqueous. Then I need to balance my equation, and if you check that out, that's balanced. So that's the molecular equation, which they didn't particularly ask me for, but it's kind of the first step in doing the net ionic equation. So next, we either want to write out the complete ionic equation or at least figure it out in our minds. And since you can't see what's going on in my mind, I'm going to write it on the screen. I look at the first compound, it's aqueous. This is an acid, and I know it's a weak acid. 2 reasons. It told me in the problem. And it's not one of the 6 strong acids. So do I write this as ions or a molecule? A molecule. Because weak acids do produce hydrogen ions, but mostly they're just the intact molecule. So this is HCHO2, aqueous. Sodium hydroxide, aqueous, not an acid. Write it as separate ions. It's my arrow. Water is a molecular compound. It's got the L liquid state symbol, so we're not going to separate that. And then here we have another ionic compound. It's aqueous, and so we've got sodium ion. and the other guy happens to be Form 8. So that would be my complete ionic equation. What are the spectators? Here I only have one spectator, it's the sodium ion. So for my net ionic equation, I'm just going to copy down the things I didn't cross out. So I have that acid, formic acid, plus hydroxide ion. Those will react to form water and these formate ions. That's my net ionic equation. Would this reaction be any different if I had used potassium hydroxide instead? Did the sodium participate really in the reaction? No. There has to be a cation with the hydroxide because you can't just have a solution of anions or cations. But what this is doesn't matter. It could be lithium, could be potassium. The reaction would be the same. Any questions?
Where's the CIE stand for?
Complete ionic equation. That's what CIE. Your book doesn't use these, but you might see NIE sometimes in our lab manual. Net ionic equation. So I just kind of made up the other one this morning. We will be doing several acid-base titrations in lab in this class. A titration is a technique in which you take a substance whose concentration you know, and you react it with another substance where you don't know the concentration. The goal is to find the unknown concentration. So we add one solution to the other until the reactants are in their stoichiometric ratio. It's called the equivalence point. I've added just enough of one solution to the other so that the reaction can be complete. And I measure how much I've added, and I can calculate the unknown concentration using stoichiometry. Now, the big question is, how do you know when you've added enough if you don't know what the concentration of that second thing is? So in an acid-base reaction, both the reactant and the product solutions are colorless, and so you really can't see anything unless you add an indicator. So there are a wide variety of chemical indicators that will change color when the solution undergoes a change in acidity. And so we'll add our substance until we see a color change, and that will signal that we've added just the right amount of stuff. So when we're doing an acid-base titration, we're adding hydroxide ions to hydrogen ions or vice versa, and when we get just the right number of each, the pH, the acidity of the solution will change and the indicator will change color. So here we have actual pictures and diagrams, drawings. So here we're using something like, well, actually sodium hydroxide. We're using sodium hydroxide to find the concentration of a hydrochloric acid solution. So in the flask we have our acid, and we're only showing the hydrogen ions because the chloride ions are spectators. So here's the hydrogen ions, and in our burette we have a sodium hydroxide solution. The sodium ions are also spectators, so we're not drawing them. So we have these hydroxide ions. So we're going to add some of this sodium hydroxide, and as these hydroxide ions come in here, they're going to meet up with those hydrogen ions and they're going to form water molecules. So this solution was acidic to start with, but as we add more and more base, it becomes less and less acidic. There are fewer hydrogen ions floating around. When we get to just the right number, so here we had 5 hydrogen ions, and here now we have 5 water molecules. We've added 5 hydroxide ions, and those reacted with all the hydrogen ions. That causes the acidity of the solution to change, and our indicator turns pink. So here we're using an indicator called phenolphthalein. That's a mouthful, and the good news is I won't require you to spell that. What?
Really?
I'm not, yeah, you don't have to know how to spell phenolphthalein. Not going to do that. No, that would be mean. That's just not even nice. Here's what this looks like without the little drawings added, right? So here it looks like we're adding water to water. And as we continue to add this, we begin to see some pink color in our solution because it's not mixed up yet. So when the sodium hydroxide first drops in here, there's a lot of sodium hydroxide right there, but then when we give it a swirl and mix it, it reacts with the hydrogen ions and the pink color goes away. When we get to the end, the whole solution will turn pink. Now that's way darker than you want your solution to be, but we'll talk about that in lab. Any questions? So let's do an example here of a calculation. So this combines acid-base reactions with solution stoichiometry. So we just learned about writing the equations, the chemical equations, but we learned the solution stoichiometry earlier. So here we have the titration of a 20 ml sample of an H2SO4 solution of unknown concentration. Requires 22.87 mils of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? The first thing we need to do, because this is stoichiometry, we need a balanced chemical equation. So we've got the formulas for the acid and the base. We've got H2SO4 and we've got KOH. So H2SO4 and KOH. We're not predicting precipitation or writing net ionic equations, so we can just leave the state symbols out of this. It makes it a little simpler. We're going to predict the products, though, by looking at an exchange of ions. So it's helpful to write the ions with their charges down below. And we're going to swap partners. And we should end up with water, which we do. There's H plus and OH minus, so there's our water. And then the other one is going to be potassium and sulfate. And when we look at the charges there, this is -2, that's +1. So we need 2 potassiums to balance the charge on 1 sulfate ion. Any questions? I'm going to erase this notes under here because we're not going to need those anymore. And I need that space for something else. Is this a balanced chemical equation?
Yes.
No. Yeah, the hydrogens are not quite, and the potassium, right? So here we've got K2, and there I've just got K. So there's hydrogens and oxygens everywhere. I like to focus on the other things first, so I'll put a 2 here. And then I've got 2 potassiums, so that's okay. I can treat the sulfate as a unit, so that's fine. Then I've got 2 hydrogens here and 2 OH here, and so that's going to give me 2 water molecules. Okay? Now I have my balanced chemical equation. I'm going to use that like I did in other stoichiometry problems to organize the information. So for sulfuric acid, I had 20 milliliters of that. We don't know what the concentration is. And it's telling me I used 22.87 milliliters of KOH, and that was 0.158, capital M. Instead of writing capital M, I'm going to write moles per liter, because that's what it means. And then what I'm trying to find is the concentration of the unknown H2SO4 solution. So question mark. And the most common units for concentration in chemistry are moles per liter. So we can assume that. So for stoichiometry, we start out with grams to moles to moles to grams. And sometimes that's good, and sometimes we need to fix it. Is that going to work for this problem? No. What are we starting out with instead of grams? We're starting out with milliliters. We'll cross that off and put milliliters. And then what do we want to find at the end? We want moles per liter, right? So we don't want grams. So if we stopped here with the moles and took moles and divided by liters of solution, we'd get the molarity. Everybody okay with that? Yeah.
So we couldn't do the M1V1 equals M2V2 here?
No, you can't do M1V1 equals M2V2. That is for dilution. This is not dilution. This is a chemical reaction. And there's a big old fat 2 in there. So the dilution equation is going to give you the wrong answer for this one. Good question.
If you multiply the concentration by 2.
Well, the thing is, you're going to have to figure out which one do I multiply by 2, or was it I should divide by 2? Way too much thinking. It's fraught with peril. Avoid at all costs. Stoichiometry should become an old friend to you, and if it hasn't become familiar yet, we need to work on that, because it's not going to go away. Stoichiometry just is like a main part of chemistry. So there's our path, milliliters to moles, and we're going to take the moles and combine with the volume of the solution to get the molarity. So I'm starting with 22.87 milliliters of KOH. And I want to go to moles of KOH, and I'm going to have liters in the denominator. And I look at that and I'm thinking, no, wait a minute. I've got a milli in there. Well, let's do this. Let's put a milli on the top and a milli on the bottom. So I've got 0.158 millimoles per milliliter. I could cancel the millis out, and that would give me this concentration. So this is the same as 0.158 millimoles, come on, divided by milliliters. Do you see how those would cancel out? Metric prefixes can be canceled like variables in algebra. So these two are exactly the same. By sticking those in there, then I don't have to mess around with converting back and forth between milliliters and liters, which a lot of people do incorrectly. Sometimes you still have to do it, other times you don't. Okay, so I went to millimoles of KOH. So next I would normally do moles of H2SO4. H2SO4. And I would put moles of KOH in the bottom. But we're using millimoles. So this is millimoles of H2SO4 to millimoles of KOH. What's the relationship between these? It's 1 to 2. 1 millimole of H2SO4 for every 2 millimoles of KOH. 1 mole to 2 moles. 1 dozen molecules to 2 dozen molecules. So millimoles of KOH cancel out. That's in red to just point out that I put milli on the top and the bottom. If you take those red things out, you get this. If you cancel those. So I'm just trying to show you that these are exactly the same thing. Once you get comfortable with millimoles, it makes a lot of calculations so much easier. So let's just see what I'm going to get if I stop here. Calculate. Got 22.87 times 0.158 divided by 2. So that's giving me 1.80673 is what my calculator tells me. And what would the unit there be? It's the only one I haven't canceled out. Millimoles of H2SO4. Well, I want moles per liter. I need to use the volume here. What's the unit on the volume? Milliliters. So if I took my millimoles and divided by milliliters, oops, it's not a 0, it's a 1. 1.80673 millimoles. I'm going to divide by the volume, 20.0 milliliters. Divide by 20. 0.0903. Let's not be ridiculous here. How many significant figures should my answer have? 3. 4's close. 3. So there's 3, and I'll write down 2 extras, and my units are millimoles per milliliter. How do I make that into moles per liter? Anybody? I just cancel the millis, right? I've got milli on the top and milli on the bottom. So those cancel out, because milli is short for times 10 to the minus 3. So I have times 10 to the minus 3 on top, times 10 to the minus 3 on the bottom. Those cancel out. Anything divided by itself is 1. So what I've got here, I'm going to round it now, 0.0903 moles per liter. Or you can write 0.0903 capital M. Any questions? You can convert milliliters to liters. Do the calculation. Convert the other milliliters to liters, and then divide. Those conversions end up canceling each other out. So another type of reaction are the gas evolution reactions. And some of these, the gas forms directly from ion exchange. An example here is potassium sulfide and sulfuric acid. The potassium and the sulfate get together, the hydrogen and the sulfide get together, and that happens to be a gas. It's not soluble in water, and it'll bubble out and smell really bad. Other reactions form a compound from the ion exchange that then decomposes into a gas. An example of that is sodium hydrogen carbonate, baking soda, plus acid gives us sodium chloride and carbonic acid, but the carbonic acid isn't stable and decomposes into water and carbon dioxide. And that's similar to the reaction when you add like vinegar or any other acid to baking soda. You get a lot of bubbling, right? The CO2 is the bubbles that are coming out. So these are the 4 types of reactants that will form or undergo gas evolution reactions. And so what I'd like you to focus on is this intermediate product and that. So if what you're going to do to predict these reactions, you just swap the ions like we've been doing. And then look at what you get. If you get H2S, you got to remember that's a gas. If you forget that, it's not going to cause you to fail the class for sure. It's not a big deal. If you get one of these guys, you should recognize that those are unstable and then write what they fall apart into. And it's actually easier than it appears at first glance because they follow a nice pattern. So carbonic acid is going to decompose. And what happens is all of these are going to have a water molecule as one of the products. So these intermediates, they each lose H2O, and the gas is whatever's left. So this is going to be H2O plus something. So I can look at that and say, well, if I remove H2O, what do I have left? Oh, I've got a mistake there. That's not H. That's supposed to be a 3. That's kind of important. Okay, H2CO3. So I'm losing H2O, so I'm going to lose both of those hydrogens, and I'm going to lose one of the oxygens, and so that's going to make this a 2. So after I remove 2 hydrogens and an oxygen from that, I'm left with CO2. Carbon dioxide, that's a gas. Same thing with these other 2. So H2SO3 forms water, and so we're going to lose the 2 hydrogens and we're going to lose one of the oxygens. So that leaves SO2. That's a gas because I told you so. And then we've got ammonium hydroxide, which does not look like those 2. Ammonium hydroxide. Oh, I didn't mean to reverse the colors, but I did. Oh well. Again, loses water. Look at the formula. Like, okay, well, I need to get rid of an oxygen, so there's the oxygen, and get rid of that. I need to get rid of 2 hydrogens, so I'll get rid of this one hanging on the end, and then I need to get rid of one of those, so that 4 becomes a 3. And I've got NH3. Ammonia is also a gas. Also, it doesn't smell good. So these 2 smell bad, that one smells bad, CO2 is the only one that doesn't stink. Any questions? Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Now here we've got a big hint. It says gas evolution reaction. Well, we're going to write the formulas for the reactants. We're going to swap ions and see what we end up with. So hydrobromic acid. The hydro in front tells me that's a binary acid. That's HBr. Aqueous. That's hydrogen ion and bromide ion. Potassium sulfite. Potassium and sulfite. What's that sulfite? SO3. And what's the charge? 2-. So the formula for this one then is K2SO3, also aqueous. I'm going to swap partners, see what happens. So I'm going to get K plus with Br minus, and put those two together. KBr. Is that soluble or insoluble? Soluble. It's potassium. All potassium compounds are soluble. And then the other combination here is H plus and SO3, 2-. So that's going to make H2SO3. I'm supposed to have a gas. One of these is going to fall apart and form a gas. Is it the KBr or the H2SO3? It's this one, H2SO3. I'm going to get rid of this down here. So this is unstable, and it's going to decompose. It's going to decompose into water, which is a liquid, and what's left when I remove water from this molecule? SO2. SO2 is my gas. So we've got information here, but it's not really in the form of a molecular equation yet. We haven't considered whether it's balanced or not. Let's balance it just with the top here without thinking about the decomposition. Is it balanced? No. What's the one that sticks out as not being balanced? Potassium. I've got K2, and here I've got just K. So I need to put a 2 here. So my potassiums are good, but now I've got 2 bromines, and over here I only have 1 bromine. So I need to put a 2 over there. My SO3, until it decomposes, is staying together. I've got SO3 over here. I've got 2 hydrogens and 2 hydrogens. So this part up here is balanced now. I only have 1 of these, and it's going to decompose into these 2 things. So I'm just going to rewrite this. 2HBr aqueous plus K2SO4 aqueous will form 2 KBr aqueous plus H2O liquid plus SO2 gas. Yes, it is K2SO3. Thank you. We use sulfate so much more frequently than sulfite that I tend to forget that. Any questions?